linear transformation here. This section is entitled Matrix Transformation. Um, what's a transformation in math? What's another name for that? Where I take something, I change its form by channeling these terms through an expression. And so if you give me A, I can give you B. If you give me x of 1, I can give you f of x of 1. Maybe you understand it like that. If I give you x of 2, you give me f of x of 2. That's a transformation, right? You give me a number or a vector, and then I can put that through a machine, and I get something else. What's that called? Function. Thank you. Thank you. Yes, it's a function. So transformation is all we're talking about is a function. Okay. Matrix transformation ends up ultimately being matrix multiplication. That's the translation of what it means. All right. So we talk about matrix transformation in the long scheme of things. This section is so watered down, it doesn't even really take my time to even have to go over this. I think in later chapters he really deals with stronger consequences for matrix transformations. We won't even get into it. We'll be too busy with Graham-Smith process and all of that, and orthogonal bases and orthonormal bases that won't have time to get over into linear or matrix transformations. We call a matrix transformation a linear transformation when one set of vectors are said to be mapped to another set. This mapping is a function. We denote functions by f. F is set to map a set of vectors. Suppose the so-called domain would be Rn. This is the Euclidean n space. To try to map those vectors, those terms, to a codomain or a range that we call here the Euclidean m space. Here's the key: by the multiplication of a matrix A. So we say formally that here this function, we call it is f here, but for matrices it's a capital T for the transformation. So the transformation on the function that maps here vectors from Rn, it goes over into Rm. How does that happen? It simply happens by a matrix A that you multiply on a vector times that matrix. You remember that depending on the various sizes of the matrices and matrix multiplication, the resulting matrix could have a different size to it. Well, the size of the matrix, the result of it, is said to be the range. And then the given vector is said to be values from your domain. So here, definition, a linear transformation is a function with domain Rn and codomain or range Rm. Then we say that that f is a linear transformation. And I don't know if I think I talk about, I don't know, in this section, this word linear, and what does that mean? We'll talk about it later on in the book, but I thought maybe it was here. It might not be. If I have a moment, I'll probably just write it down for you. So here, this mapping of a function that takes a value from the domain. The same thing back in Math 112, when you had a function and they asked the question, what's the domain, what's the range? And it's the same idea here. So can you find, given a particular mapping, a given transformation or given function, if you will, can we determine the size of the domain, and then also the size of the range. And that's all he gets at in this section. Oh, beautiful. This theorem here, both working together, really one of the same. This theorem, folks, is the definition of a linear algebra. This is what we've been trying to get to, and we're going to stay here for the rest of our lives. A linear algebra. What's a linear algebra? A linear algebra is any set of functions or vectors whereby if I operate on the sum, whatever the operation is, if I operate on the total, that equals to the operation on the individual terms. Now, what's the operation? It could be anything. For you, you've had calculus. Operation could be the derivative. The derivative of the sum is equal to the sum of the individual derivatives, right? You see what I'm talking about? Do you remember in calculus where we said that the derivative with respect to x of f of x plus or minus g of x? Remember when we said that? We said that this is equal to, here, the derivative of f of x plus the derivative of g of x. Well, maybe it wasn't written like that. It could have been, say for example, maybe you saw it like this. You see this is f prime of x plus g prime of x. Right. Example. If f of x is equal to x, don't want to make that x to the x, that's an interesting function. Say x squared, and then g of x is equal to 2x to the fourth. Now, if we look at them together, f plus g of x is equal to x squared plus 2x to the fourth. So if I take the derivative of f plus g of x, this is the same thing as 2x plus 8x to the third. But isn't that the same thing as f prime of x plus g prime of x? Where f prime of x, f prime is 2x, and g prime is 8x to the third. Right? You remember that, right? Well, the only reason that you were able to do that is because functions, polynomials, are set to be a linear algebra. That's the statement here, that the transformation, here A is the matrix A, the transformation of two vectors, u plus or minus v, is said to be the transformation here of matrix multiplication of A on u plus or minus the transformation on v. And whether or not the matrix A is readily known, if it's not, then we write it in the general sense That's the theorem down below here. And we call them two things. We call them additivity and homogeneity. Additivity means that I can take the transformation of the sum, and that's equal to the sum of the transformations. Whether it's a sum or a difference, we still call it additivity, right? Whether you're adding in the positive direction or negative direction, you're still adding. And then homogeneity, that the transformation is not obstructed because of a scalar. So it could be the scalar inside of the transformation. What's the transformation? It's the matrix. So if I have a scalar multiplied to each term in the matrix, I can take that scalar out and say it's the scalar number times the entire matrix. Does not offset the matrix. So if you're row reducing, if you're finding the inverse, you can manipulate that matrix by pulling out in some kind of way that common factor. We call that homogeneity. Now, has anybody taken differential equations yet? Right? So you've had that. You've had that. Okay. Huh? You're taking it now. Okay. So by now, you should have ran across the notion of a homogeneous differential equation, right? And in the beginning of that homogeneous expression, an example is to be able to show, let me write it down. Is to be able to show that f of t x ty is the same thing as t to the n times f of x comma y. Right? So that it comes from linear algebra. Because the differential equation is also a linear algebra. You know, there's a chart that is known that says this mathematical idea gives you these courses that you study. They all come from this big umbrella. So linear algebra, beneath it you have calculus, algebra, trigonometry, differential equations, right? And then even above the linear algebra, there are other forms out there. Right? There's something that we call topology, something that we call the analysis structures, and there's something that's called combinatorics. In combinatorics, we have number theory and permutations, and we get statistical analysis and all of that. So what we're studying and what you've been studying, basically all of your days, even going back to kindergarten, has been linear algebra. They didn't tell you that. That's what you've been studying. Let me make one more statement, then we'll work these very simple problems. Here that the translation of 0, if I multiply a matrix A by 0, then you're supposed to get the 0 matrix. That's what this is saying here. So 0 should map into itself. Find the domain and range, codomain of the transformation. So the domain is where I'm coming from. The range is where I'm going. So the domain here for linear transformations is said to be the size of the matrix that I'm given. Now, the matrix that you're given will be the matrix here that involves x sub 1, x sub 2, and x sub 3. And times some matrix coefficient A multiplication, and then the result, I get values of W. I'm going to write that out so you can see it for one time here, and then for the rest of the problems, you can just kind of go at it directly. I want you to see what this transformation is saying. I have this transformation on A where you're said to be mapping from a vector space. There's said to be some Rn that's here going into another vector space, Rm. if n is equal to m, we call that an operator. I think I said that here. I didn't say it, but I wrote it here, a special case, that if n is equal to m, we call the transformation an operator. And that's basically what you get in calculus. I want to take this statement here and translate it based on what we're given here. I want you to see it. All right. So here's what this says. This says that I have a matrix that I'm multiplying. Multiplying what? I'm multiplying whatever given vector that I'm given. With the result, let's check this out. This is a 3 by 3. This is a 3 by 1. So the result has to be another 3 by 1. What's in this 3 by 1 resulting matrix? W sub 1, W sub 2, W sub 3. I want you to see here that this is the matrix A for this transformation, basically, and here, these guys are my domain values. And here, my codomain or a range. So the transformation simply says, you give me a vector, anything, x sub 1, x sub 2, x sub 3, and then I can give you, by multiplying that vector times the matrix A, I can transform it, and I get something now in the function result, right? So the size of the domain is set to be R3, right? This is a 3-tuple vector. So our domain here is R3, and our range or codomain is also of 3 dimension. Right? So that would be an operator. All right. So look here. This matrix here is a 3 by 2, and this vector here is a 2 by 1, which the resulting matrix would be a, do you see it? It's going to be a 3 by 1. So the domain is this size, right? This is our range size or dimension. So here our domain would be R2, and our range would be R3. Does that make sense? Okay. Same thing here. These values here give us our domain. It's a 3-tuple, so it's R3. Let's count this up. Now, what's our range? That's right, it's size 2. Right? There's only 2 vectors there. Here, our domain would be a 3-dimensional vector. And then what about our range? 4. 1, 2, 3, 4. Very good. That 0 is important for space position. I think you get it. Any questions? Well, I have 10 minutes, but the next section is very long, so I'll reserve on Monday to go over section 1.9. On Wednesday, we're going to cover section 1.10. It's very short, basically just one problem, and then I'll review. Then the following Monday, we'll take test number 2. Okay? Thank you.